Listen, I need you to forget everything you think you know about the universe for the next 3.5 hours. Because what I'm about to share with you isn't just another space discovery. This is the moment when humanity's entire cosmological model started cracking at the seams. On July 12, 2022, when James Webb Space Telescope released its first images, astronomers around the world weren't just excited. They were terrified, not because of what they saw in those stunning pictures of distant galaxies, but because of what those galaxies shouldn't have been doing. They shouldn't have existed at all. Not there, not then, not like that. Here's what nobody is telling you. Those early galaxies are too massive, too mature, too structured for the age they're supposed to be. It's like finding a fully grown oak tree in a nursery that opened yesterday. And this isn't a small problem we can patch up with a new equation. This is a fundamental crisis that suggests our entire understanding of cosmic evolution might be catastrophically wrong. The Hubble constant, the number that tells us how fast the universe is expanding, is giving us two completely different answers depending on how we measure it. One method says the universe is expanding at 67 kilometers per second per megaparsec. Another method says 73. That doesn't sound like much, right? Wrong. That's like measuring the distance from New York to Los Angeles and getting answers that differ by the width of Texas. In cosmology, this is called the Hubble tension, and it's the kind of discrepancy that breaks entire theories. But here's where it gets absolutely mind-bending. James Webb has found galaxies that existed just 300 million years after the Big Bang that look like they've been around for billions of years. They have complex structures, heavy elements, supermassive black holes. The universe at that age should look like cosmic baby food, formless and simple. Instead, Webb is showing us a universe that hit the ground running, fully formed, as if someone hit fast forward on cosmic evolution. What if the Big Bang wasn't the beginning? What if the universe is older than we thought? What if dark energy is changing? What if we're living in a cosmos that operates on rules we haven't even imagined yet? Before we dive deeper into this existential crisis, I need you to do something. Hit that like button right now. Seriously, because what you're about to learn over the next few hours is going to fundamentally alter how you see reality, and I need to know this message is reaching people. Subscribe if you haven't already, and drop a comment telling me which country you're watching from and what time it is where you are. I want to know how far across this planet this revelation is spreading. Are you watching this at midnight, unable to sleep because your mind is already racing? Or is it morning and you're about to have your entire day derailed by what you're about to discover? Now, let's start from the beginning, but not the beginning you think. To understand why James Webb's discoveries are shattering our cosmic worldview, you need to understand what we thought we knew. And trust me, the story of how we built our model of the universe is just as shocking as the story of how it's all falling apart. In 1929, an astronomer named Edwin Hubble made a discovery that should have won him a Nobel Prize, but didn't because the committee didn't believe it was real. He found that galaxies weren't just sitting still in space. They were moving away from us. All of them. And the farther away they were, the faster they were receding. It was as if the entire universe was expanding, stretching like a balloon being inflated. Think of it like this. Imagine you draw dots on a deflating balloon, then start inflating it. Every dot moves away from every other dot, and the dots that were farther apart move away from each other even faster. That's our universe. Hubble had discovered cosmic expansion. But here's the twist nobody tells you about. Hubble's original calculation of the expansion rate was off by a factor of 7. 7. He thought the universe was expanding 7 times faster than it actually is, which would have made the cosmos younger than the rocks on Earth. The error came from misidentifying the types of stars he was using as cosmic measuring sticks. For years, our entire cosmological model was built on a foundation that was spectacularly wrong, and nobody knew it. This should tell you something crucial. we've been wrong before, catastrophically wrong, about the most fundamental measurements in cosmology. Keep that in mind. So we fixed Hubble's error, refined our measurements, and built the Lambda CDM model, the standard model of cosmology. Lambda represents dark energy, the mysterious force causing the universe to expand faster and faster. CDM stands for cold dark matter, the invisible substance that makes up 27% of the universe's mass energy content, but has never been directly detected. Regular matter, everything you can see and touch, every star, planet, and galaxy, is only 5% of the universe. The rest is these two mysterious components we've never actually isolated or understood. Let me be clear about how insane this is. We've built our entire cosmic model on the assumption that 95% of the universe is made of stuff we've never seen, never touched, never captured in any detector. We know dark matter exists because of its gravitational effects. Galaxies spin too fast. They should fly apart based on the visible matter alone, but they don't. Something invisible is holding them together. We call it dark matter because we literally have no idea what it is. It's a placeholder name for our ignorance. Dark energy is even more bizarre. In 1998, two teams of astronomers, led by Saul Perlmutter, Adam Rees, and Brian Schmidt, discovered something that won them the Nobel Prize and broke physics. They were measuring distant supernovae, using them as standard candles to map cosmic expansion, expecting to find that the expansion was slowing down due to gravity. Instead, they found the expansion was speeding up. The universe isn't just expanding, it's accelerating. Something is pushing space itself apart, working against gravity, and we have absolutely no idea what it is. Dark energy makes up 68% of the universe. It's the dominant component of reality, and we know nothing about it except that it exists and it's winning a war against gravity that will eventually result in every galaxy beyond our local group being pushed away from us faster than light can travel, leaving our descendants in a universe that appears to contain only one galaxy, our own. The cosmos will become an island of light in an infinite ocean of darkness. Here's what will blow your mind. That's the standard model. That's the one we're confident about. That's what we teach in universities. And James Webb just found evidence that even this bizarre, improvised model might be completely wrong. But before we get to what Webb found, you need to understand how we measure cosmic distances and ages. Because when you understand the method, you'll understand why the discoveries are so catastrophic. The cosmic distance ladder is one of humanity's greatest intellectual achievements, and it's also incredibly fragile. We measure nearby stars using parallax, the apparent shift in position as Earth orbits the Sun. Think of it like closing one eye and holding your finger up, then switching eyes. Your finger appears to jump against the background. That jump gets smaller the farther away something is. We can use this to measure distances to stars within a few hundred light years. For farther distances, we use Cepheid variable stars, stars that pulse with a regular rhythm, and the period of their pulsation is directly related to their intrinsic brightness. Henrietta Swan Leavitt discovered this relationship in 1912, and it became the foundation of cosmic distance measurement. If you know how bright a star actually is, and you measure how bright it appears, you can calculate how far away it is. Simple geometry. For even greater distances, we use Type Ia supernovae, exploding white dwarf stars that all reach roughly the same peak brightness. They're like cosmic lighthouses with a standard wattage. When you see one go off in a distant galaxy, you can calculate that galaxy's distance. This ladder of techniques, each one building on the previous rung, allows us to measure distances across billions of light years. But here's the problem. Each rung introduces uncertainty. Each step requires calibration. And if your first rung is off, every subsequent measurement is wrong. The Hubble tension is telling us something is fundamentally off with this ladder. When we measure the expansion rate using the distance ladder, looking at relatively nearby supernova and working our way up, we get one answer: 73 kilometers per second per megaparsec. When we measure it using the cosmic microwave background, the afterglow of the Big Bang, using completely different physics from the early universe, we get 67. That 9% difference might not sound catastrophic, but in cosmology, it's a chasm. These methods should agree. They're measuring the same universe, the same expansion. The fact that they don't means either our measurements are wrong, our understanding of the early universe is wrong, our understanding of cosmic evolution is wrong, or reality is weirder than we ever imagined. Adam Rees, one of the Nobel laureates who discovered dark energy, has spent years refining measurements, trying to make this tension go away. It hasn't. He's used Hubble Space Telescope to directly measure Cepheid variables in galaxies out to record distances. He's calibrated and recalibrated. The tension remains. In fact, it's gotten worse. The more precise our measurements become, the more certain we are that something is deeply wrong. And then James Webb started observing. The first thing Webb did was look at the same Cepheid variables Hubble had been studying, but with unprecedented clarity. Webb's infrared vision can peer through cosmic dust that obscures these stars, giving us the cleanest measurements ever. What did Webb find? The high expansion rate was confirmed. The tension is real. This isn't a measurement error. This is reality telling us our model is broken. But that's just the warm-up. That's just confirming the problem. What Webb found next is the part that's causing existential dread among cosmologists. Remember, the universe is 13.8 billion years old, according to our models. The first stars and galaxies should have formed slowly, gradually, over hundreds of millions of years. The early universe should be simple, primitive, messy. Small galaxies forming, merging, building up over cosmic time into the massive, mature galaxies we see today. James Webb looked at the universe just 300 to 500 million years after the Big Bang. That's 2% of the universe's current age. That's cosmic infancy. And what Webb saw shouldn't exist. GLASSZ13, a galaxy spotted by Webb, exists just 300 million years after the Big Bang. It's massive. It's bright. It contains complex structures. The light from this galaxy has been traveling for 13.5 billion years to reach us, and we're seeing it as it appeared when the universe was barely out of the cosmic cradle. But here's the problem. According to our models, galaxies this massive shouldn't be able to form that quickly. The standard theory of structure formation says that matter starts clumping together due to tiny density fluctuations in the early universe, enhanced by dark matter's gravity. Small clumps form first, then merge into larger clumps, building up over hundreds of millions of years. It's a bottom-up process, slow and gradual. These Webb galaxies are telling us the universe didn't have time to build bottom-up. It's as if someone assembled fully formed galaxies right out of the gate. Mike Boylan-Colgan, an astrophysicist at the University of Texas, ran simulations and found that these early massive galaxies are barely permissible under our current models. And that's the polite academic way of saying they shouldn't be there. What if I told you it gets worse? Some of these early galaxies don't just have stars. They have supermassive black holes. Black holes millions or billions of times the mass of our sun, sitting at the centers of these infant galaxies. We found quasars, galaxies powered by actively feeding supermassive black holes at similar cosmic epochs. These black holes are already billions of solar masses when the universe is barely 500 million years old. How? Our models say supermassive black holes form the deaths of massive stars whose remnants collapse and then slowly accumulate matter over billions of years, growing gradually from stellar mass black holes into the monsters we see today. But these early universe black holes don't have billions of years. They have hundreds of millions. It's like watching an acorn turn into a giant oak in fast forward, except even faster. Priyamvada Natarajan, a theoretical astrophysicist at Yale, has proposed that maybe these black holes didn't form from stars at all. Maybe they formed directly from collapsing gas clouds in the early universe, born massive. But even that requires special conditions we haven't observed and don't fully understand. Every explanation requires us to add new physics, new assumptions, new exceptions to our rules. Here's what keeps cosmologists up at night. We might be looking at a universe that doesn't play by the rules we thought governed cosmic evolution. Either structure formation was vastly faster than we believed possible, or the early universe had conditions we never anticipated, or our timeline is wrong. What if the universe is older than 13.8 billion years? What if the Big Bang wasn't the absolute beginning, but a transition from some earlier state? What if the expansion rate has changed over time in ways we haven't accounted for? Every time we try to fix one problem, we create three more. It's like pulling a thread on a sweater and watching the whole thing unravel. And we're just getting started. Because what Webb found about galaxy shapes is even more disturbing. In our models, early galaxies should be messy, irregular, chaotic. They're newly formed, still settling down, frequently colliding and merging. They should look like cosmic train wrecks. Instead, many of Webb's early galaxies show disk structures, spiral arms, organized shapes. They look mature. Erica Nelson, an astronomer at the University of Colorado, studied Webb images and found galaxies with clear disk structures at redshifts, indicating they existed less than 1 billion years after the Big Bang. She called them universe breakers because they break our models of how galaxies assemble. Think of it like this. Imagine you're watching a time-lapse of a city being built. You expect to see foundations, and frames, and walls, and roads, a gradual construction over time. Instead, you see empty land, then blink, and there's a fully formed city with roads, buildings, infrastructure, as if it teleported into existence. That's what Webb is showing us. The standard model predicts the cosmic dark ages, a period after the Big Bang when the universe was filled with neutral hydrogen gas that absorbed light, before the first stars formed and reionized it. This period should last from about 380,000 years to a few 100 million years after the Big Bang. But if galaxies are forming massive structures by 300 million years, the dark ages were way shorter than we thought. Reionization, the process where the first star's ultraviolet light ionized the hydrogen gas, making the universe transparent again, had to happen fast, really fast. Too fast for our models to easily accommodate. What's causing this sinking feeling among cosmologists is the realization that we might need to throw out decades of carefully constructed theory and start over, not tweak it, not adjust parameters. Start over. At this point, you might be thinking, okay, but scientists are wrong all the time, and they fix their theories. Why is this different? Because this isn't one anomaly. It's multiple independent lines of evidence, all pointing to the same conclusion. Our cosmic model is incomplete at best, wrong at worst. The Hubble tension, the early massive galaxies, the supermassive black holes, the mature structures, all of it paints a picture of a universe that doesn't match our equations. Let me ask you something. What does it mean that we can send robots to Mars, predict eclipses centuries in advance, build quantum computers, but we can't explain what makes up 95% of the universe, or why it's expanding the way it is? What does that tell you about the limits of human knowledge? We're 3,000 years removed from ancient Greeks, who thought the Earth was the center of everything. We're 500 years past Copernicus, who displaced us from the center. We're 100 years past Hubble, who showed us the universe is expanding. And now, we're potentially on the verge of another revolution that will make all of those look like minor corrections. Here's your first retention oak, the thing that should make you keep watching. What if I told you that some physicists now believe dark energy isn't constant? That it might be changing over time, evolving, and if that's true, the fate of the universe is completely up for grabs? We're going to explore that in the next section, and it's going to fundamentally alter how you think about the future of reality itself. But first, let me connect something for you. All of these discoveries, all of this cosmic confusion, it's happening because we finally have the right tool for the job. James Webb isn't just a better Hubble. It's a different kind of instrument entirely. And understanding why it can see what Hubble couldn't is crucial to understanding why these discoveries matter. The James Webb Space Telescope is the largest, most powerful space telescope ever built. Its primary mirror is 6.5 meters across, compared to Hubble's 2.4 meters. That's not just bigger. That's 7 times the light collecting area. But size isn't the revolutionary part. Wavelength is. Hubble observes primarily in visible and ultraviolet light, the same light your eyes see. Webb observes in infrared heat radiation. Why does this matter? Because the universe is expanding. When light from distant galaxies travels billions of years through expanding space, the wavelength of that light gets stretched. Blue light becomes red light. Ultraviolet becomes visible. Visible light becomes infrared. The farther away a galaxy is, the more its light is redshifted. The most distant galaxies, the ones from the early universe, have had their light stretched so much that their original ultraviolet and visible light has been pushed all the way into the infrared. Hubble can't see far infrared. Its instruments weren't designed for it, and Earth's atmosphere glows brightly in infrared, blocking ground-based infrared telescopes. But Webb, sitting at a gravitational balance point a million miles from Earth, with a giant sunshield keeping its instruments at minus 370 degrees Fahrenheit, can see infrared with unprecedented clarity. That means Webb can see the earliest, most distant galaxies that are completely invisible to Hubble. It's like putting on night vision goggles in a dark room and suddenly seeing a world that was there all along but hidden. And what Webb sees in that hidden world is breaking our brains. Let me give you a moment to process this, because we're about to go deeper. You're 20 minutes in. If you're still with me, you're the kind of person who doesn't accept easy answers. You want to know how reality actually works, even if the answer is uncomfortable. That's rare. That's valuable. Make sure you're subscribed, because this journey gets stranger from here. Now, let's talk about what happens when you take the most sophisticated cosmic measuring device ever built and point it at something we thought we understood: galaxy formation itself. In our standard model, galaxies form through a process called hierarchical assembly. Small structures form first, merge together, form bigger structures, which merge, and so on, building up the massive galaxies we see today over billions of years. It's an elegant theory, supported by computer simulations, mathematical models, and decades of observations. Webb just found galaxies that seem to have skipped the entire process. In February 2023, a team led by Ivo Lab published findings about 6 massive galaxy candidates from Webb data, dating to 500 to 700 million years after the Big Bang. These galaxies appeared to be so massive, so evolved, that Lab himself said they shouldn't exist, according to current theories. The mass estimates from these galaxies suggested they contained as many stars as our Milky Way, but they'd had only a fraction of the time to assemble them. To pack that many stars into such an early epoch, the star formation rate would have had to be absurdly high, converting almost all available gas into stars with near-perfect efficiency. Now, here's where it gets interesting. Some of these galaxy candidates might be other things. Active galactic nuclei, supermassive black holes feeding on material, can mimic the appearance of massive starlight. Further observations are still being analyzed. But even if half of these candidates are misidentified, even if we've overestimated their masses, the problem remains. There are too many massive, evolved galaxies in the early universe. Joel Leah, an astronomer at Penn State who worked on the analysis, put it bluntly: we found something we never thought we'd find. Think about what that means. Astronomers expected to be surprised by details, by specific features, by individual weird objects. But they didn't expect the entire population of early galaxies to be fundamentally different from predictions. That's not a detail. That's a paradigm failure. And here's where we need to talk about what a paradigm failure actually means in science, because this is important for understanding why this discovery is causing such upheaval. In 1962, Thomas Kuhn published The Structure of Scientific Revolutions, where he introduced the concept of paradigm shifts. Normal science, he argued, works within a paradigm, a framework of assumptions and methods that everyone agrees on. Scientists solve puzzles within that framework, refining details, making measurements more precise. But sometimes, anomalies accumulate, things that don't fit. At first, scientists explain them away, tweak the model, add epicycles. But eventually, the anomalies become so numerous, so fundamental, that the paradigm itself collapses and a revolution occurs. A new paradigm emerges that explains both the old data and the new anomalies. We've been living in the lambda CDM paradigm for decades. It's been our framework. But the Hubble tension, the early massive galaxies, the rapid structure formation, these aren't small anomalies we can explain away. These are cracks in the foundation. What comes next? Nobody knows. That's the terrifying and exhilarating part. We're potentially living through a paradigm shift in real time, and nobody can predict what the new paradigm will look like. Some physicists are proposing that dark energy isn't constant. The cosmological constant, Einstein's lambda, might not be constant at all. It might be a field that changes over time, called quintessence. If dark energy is evolving, the expansion rate of the universe has changed throughout cosmic history in ways we haven't accounted for. And our age estimates, our distance calculations, everything could be off. Other physicists suggest early dark energy, a burst of additional dark energy in the first moments after the Big Bang that rapidly accelerated structure formation, allowing galaxies to form faster. But this introduces new fine-tuning problems and raises more questions than it answers. Still others are questioning whether our understanding of gravity is correct on cosmic scales. Modified Newtonian dynamics, MOND, and other alternative gravity theories try to explain cosmic observations without dark matter and dark energy. Most physicists are skeptical because these theories have their own problems and don't fit the data, as well as lambda CDM in most cases. But if lambda CDM is failing, maybe it's time to revisit alternatives. Here's what will blow your mind. We might be facing a crisis similar to what physicists faced in the early 20th century when quantum mechanics and relativity overturned classical physics. Back then, experiments gave results that made no sense in the Newtonian framework. Light behaved like both a wave and a particle. Time was relative. Space could curve. These weren't tweaks to Newton's laws. These were completely new frameworks. We might need a completely new framework for cosmology. Not lambda CDM version 2.0, but something fundamentally different that we haven't imagined yet. And this brings us to one of the most unsettling possibilities of all. What if the universe we observe is older than the Big Bang we've identified? The Big Bang model says the universe began 13.8 billion years ago in an incredibly hot, dense state and has been expanding and cooling ever since. But what if the Big Bang wasn't the beginning? What if it was a transition? Conformal cyclic cosmology, proposed by Nobel laureate Roger Penrose, suggests the universe goes through infinite cycles. Each cycle ends in a state that becomes the Big Bang of the next cycle. In this model, our Big Bang had a predecessor, and the structures we're seeing in the early universe might be echoes or remnants from a previous cycle. Eternal inflation, proposed by Alan Guth and others, suggests our Big Bang was just one bubble in an eternally inflating multiverse. Different bubbles, different universes, could have different physics, different ages, different histories. Maybe what we're seeing is evidence that our bubble's conditions were different than we thought, seeded by processes from the larger inflationary landscape. These aren't fringe ideas from cranks. These are serious proposals from leading physicists trying to make sense of observations that don't fit. Here's the thing. Cosmology has always been a field where imagination and rigor dance together. We're trying to understand the origin, evolution, and fate of everything using mathematics, physics, and observations from a tiny rocky planet orbiting an average star in an ordinary galaxy. The audacity of that endeavor is either inspiring or absurd, depending on your mood. But we've been successful before. We predicted the cosmic microwave background before we observed it. We predicted the abundance of like elements created in the Big Bang and found them. We predicted gravitational waves and detected them a century after Einstein proposed them. When our theories work, they work spectacularly. The question is, are we in a period where our theories are about to spectacularly fail? Let me give you something to think about as we transition to the next phase of this journey. Every generation of scientists has believed they were close to a complete understanding of the universe. Victorian physicists thought they'd figured everything out except a few details. Then came relativity and quantum mechanics, and their entire worldview collapsed. We're not immune to that same hubris. In fact, we might be more vulnerable because our tools are so good. We've convinced ourselves we're seeing clearly. But maybe James Webb, our most advanced tool yet, is showing us just how much we've been missing. You're 40 minutes in. Here's what's coming next. We're going to explore what these discoveries mean for dark matter and dark energy, those mysterious components that make up 95% of the universe. Because here's the thing nobody's telling you. If our cosmic timeline is wrong, our understanding of dark matter and dark energy is wrong too. And if those are wrong, we literally don't understand what most of reality is made of. Stay with me. This is where it gets truly mind-bending. Dark matter is supposed to be everywhere. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all. The only way we know it exists is through gravity. Galaxies spin too fast. Galaxy clusters have more mass than we can see. Gravitational lensing, the bending of light around massive objects, shows more mass than visible matter can account for. Fritz Zwicky first proposed dark matter in 1933 when he studied the Coma cluster and found galaxies moving so fast they should have escaped the cluster's gravity unless there was much more mass than he could see. He called it Dunkel Materie, dark matter. Nobody took him seriously for decades. Then in the 1970s, Vera Rubin measured rotation curves of galaxies and found that stars at the edges of galaxies were moving just as fast as stars near the center, which made no sense. Gravity should weaken with distance, so outer stars should move slower. Unless there was a massive halo of invisible matter surrounding the galaxy, providing extra gravity. Rubin's work, along with observations from many other astronomers, convinced the scientific community that dark matter was real. Not just a quirk of one galaxy or cluster, but a fundamental component of every large structure in the universe. We've built the entire lambda-c DM model on the assumption that dark matter is cold, meaning it moves slowly compared to the speed of light, and it clumps together on small scales, seeding the formation of galaxies and larger structures. Computer simulations using cold dark matter beautifully reproduce the web-like structure of the universe we observe, vast filaments of galaxies separated by cosmic voids. But here's what they don't tell you in popular science. We have never, ever detected a dark matter particle directly. We've built incredibly sensitive detectors deep underground, shielded from cosmic rays, waiting for a dark matter particle to interact with normal matter. Nothing. We've run the Large Hadron Collider, smashing protons together at enormous energies, hoping to create dark matter particles. Nothing. We've proposed candidate particles, WIMPs, weakly interacting massive particles, axions, sterile neutrinos. We've spent billions of dollars and decades of research trying to find them. And we've found nothing. Now, that doesn't mean dark matter doesn't exist. It might just mean it's even more elusive than we thought, or it's a different kind of particle that our current models predict. But combined with what James Webb is showing us, it raises an uncomfortable question. What if our entire dark matter framework is solving the wrong problem? Let me explain what I mean. Dark matter was introduced to explain why galaxies don't fly apart and why structure formation works the way it does. It's a gravitational fix to a gravitational problem. But what if gravity itself works differently than we think on cosmic scales? Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in 1983, suggests that at very low accelerations, like those experienced by stars in the outer parts of galaxies, gravity behaves differently than Newton's and Einstein's equations predict. Instead of needing dark matter, you just need to adjust how gravity works. MOND has had some success explaining galaxy rotation curves without dark matter, but it struggles with galaxy clusters, gravitational lensing, and the cosmic microwave background. Most physicists reject MOND because it doesn't work as well as dark matter for most observations. But here's where it gets interesting. What if MOND is partially right and dark matter is partially right? What if we need both a modification to gravity and some form of dark matter? What if reality is more complicated than either framework alone can handle? Eric Verlinde, a theoretical physicist, proposed emergent gravity in 2016, suggesting gravity isn't a fundamental force, but an emergent phenomenon arising from quantum information. In his framework, what we interpret as dark matter is actually an effect of how information is stored on the cosmic horizon. It's a radical idea that most physicists are skeptical of, but it's attempting to address the same fundamental question. Why does our gravity model fail on cosmic scales? And now James Webb is throwing a wrench into all of it. If the early universe was forming structures faster than our dark matter models predict, maybe dark matter doesn't behave the way we thought. Maybe it's warmer than we assumed, moving faster, clumping differently. But warm dark matter has its own problems fitting other observations. Or maybe the early universe had more dark matter than later epochs. Maybe the ratio of dark matter to regular matter has changed over cosmic time. But that requires new physics for how dark matter behaves or decays, and we have no evidence for such processes. Every solution creates new problems. It's like playing cosmological whack-a-mole. And then there's dark energy, which is even more mysterious than dark matter. In 1917, Einstein added the cosmological constant to his equations of general relativity because he believed the universe was static, neither expanding nor contracting. He needed a repulsive force to balance gravity's attraction. When Hubble discovered cosmic expansion, Einstein reportedly called the cosmological constant his biggest blunder and removed it. But in 1998, when Perlmutter, Rees, and Schmidt discovered that the universe's expansion was accelerating, the cosmological constant came roaring back. Suddenly, we needed a repulsive force again, not to keep the universe static, but to explain why it was expanding faster and faster. We call it dark energy now, and we quantify it with the cosmological constant lambda, but we have no idea what it actually is. Is it a property of space itself? Vacuum energy from quantum fluctuations? Is it a new field permeating the universe? Is it something else entirely? The vacuum energy calculation from quantum field theory gives a prediction for dark energies, strength that's wrong by 120 orders of magnitude. That's not a typo. Our best quantum physics predicts a value for dark energy that's 10,120 times larger than what we observe. That's the worst prediction in the history of physics, and we have no explanation for the discrepancy. So we just accept that dark energy exists. We measure its effects, and we plug it into our equations as a constant. Problem solved, right? Not even close. Because now there's growing evidence that dark energy might not be constant. It might be changing over time. The Hubble tension, that 9% discrepancy between local and early universe measurements of the expansion rate, could be explained if dark energy was stronger in the past or weaker in the past, changing the expansion history in ways our constant lambda model doesn't account for. Several teams have analyzed supernova data, baryon acoustic oscillations, sound waves in the early universe frozen into galaxy distributions, and other measurements, finding hints that dark energy's strength has varied over cosmic time. The evidence isn't conclusive yet, and different datasets give conflicting results, but the possibility is there. If dark energy is variable, if it's a field called quintessence that evolves, the implications are staggering. The fate of the universe is completely uncertain. In our standard model with constant dark energy, the universe will expand forever, accelerating eternally, until every galaxy beyond our local group is pushed away faster than light, leaving us in cosmic isolation. Eventually, stars will burn out, black holes will evaporate, and the universe will approach maximum entropy, a state of perfect cold darkness called the heat death. Trillions upon trillions of years from now, but inevitable. But if dark energy is changing, all bets are off. If it's getting stronger, we might face a big rip, where dark energy becomes so powerful it tears apart galaxies, then stars, then planets, then atoms, then subatomic particles, ripping the fabric of space-time itself. If it's getting weaker, we might eventually see a big crunch, where dark energy diminishes, gravity wins, and the universe collapses back on itself. Or it could oscillate, weakening and strengthening cyclically, leading to a universe that expands and contracts forever, which brings us back to Penrose's conformal cyclic cosmology. The point is, we don't know. And James Webb is showing us we don't know even more than we thought. Here's what keeps me up at night, and what should keep you up too. We're living in a universe where 68% is dark energy we don't understand. 27% is dark matter we've never detected. And we're now discovering that our models for how the remaining 5% evolved are probably wrong. We're like ancient cartographers who've mapped 5% of the world and declared we understand geography, only to discover the remaining 95% doesn't follow any of the rules we thought applied to land and sea. Think of it like this. Imagine you're a detective investigating a crime scene. You found 5% of the evidence and built an entire theory of the crime around it. You're confident. The theory fits the evidence perfectly. Then you find the other 95% of the evidence, and it suggests something completely different happened. Not just details you got wrong, but the fundamental nature of the crime itself. That's where we are with cosmology. We built lambda CDM around the 5% we can see, making assumptions about the 95% we can't. And now our best telescope is telling us those assumptions might be fatally flawed. Here's your second retention hook. What if I told you that some physicists now believe we might be living in a simulation? Not because they're sci-fi fans, but because the fine-tuning of cosmic constants and the weirdness of quantum mechanics suggest our universe's parameters were deliberately chosen? We'll explore that mind-bending possibility and its connection to these discoveries later. But first, we need to talk about something even stranger. What Webb is telling us about the very first stars that ever existed. You're an hour in. You're doing something most people won't do. Sitting with uncertainty, engaging with ideas that challenge everything you thought was solid ground. That's intellectual courage. Comment below and let me know. Are you starting to feel that vertigo that comes from realizing how little we actually know? Because it gets more disorienting from here. Let's talk about population 3 stars. These are the first stars, the ones that formed from the pristine hydrogen and helium created in the Big Bang before any heavy elements existed. We've never observed one. They should have all died billions of years ago, their lifetimes measured in millions of years, because they were so massive and burned so hot. But their existence is fundamental to our understanding of cosmic chemical evolution. These first stars forged the first heavy elements in their cores and scattered them across space when they exploded as supernova. Those elements became the building blocks for the next generation of stars, which created more elements, and so on, building up the periodic table over billions of years. Our sun is a third-generation star, maybe fourth. It contains elements that could only have been created in previous stars. Your body, every atom heavier than hydrogen and helium, was forged in the heart of a star that died before our solar system formed. Carl Sagan's famous line, "We are made of star stuff," isn't poetry. It's literal truth. But this process takes time. Population 3 stars form, live, die, enrich space with heavy elements. Population 2 stars form from that enriched gas, create more elements, die. Eventually, population I stars, like our sun, form from gas enriched by multiple generations. According to our models, this should take hundreds of millions to billions of years. The early universe should be metal poor, where metal in astronomy means any element heavier than helium. James Webb has found galaxies in the early universe that already show signs of heavy element enrichment. Spectroscopy, breaking light into its component wavelengths, reveals absorption and emission lines from elements like carbon, oxygen, silicon, created in stars. These signatures appear in galaxies less than 500 million years after the Big Bang. That means stellar evolution, the full life cycle from formation to death to enrichment, happened incredibly fast. Multiple generations of stars lived and died in the first few 100 million years. Our timeline for stellar evolution might be wrong, or conditions in the early universe allowed for faster cycles. Alternatively, maybe the first stars were more massive than we thought, burning through their fuel faster, dying sooner, enriching space more rapidly. But very massive stars are rare in today's universe. Why would they be common in the early universe? Or maybe population 3 stars formed in environments so different from anything today that our entire framework for stellar evolution doesn't apply to them. Maybe the early universe was a cosmic Wild West where the rules were different. Here's something that will absolutely blow your mind. We're searching for direct evidence of population 3 stars using Webb, looking for their unique spectral signatures in the most distant, earliest galaxies. If we find one, it would be like discovering a living dinosaur. These stars shouldn't still exist. But if the early universe behaved differently than we think, maybe some survived longer, or maybe we'll see their light from cosmic epochs closer than we expected. In 2022, a team reported a possible detection of a population 3 star in a gravitationally lensed early galaxy, but the analysis is still being debated. If confirmed, it would rewrite our understanding of stellar evolution entirely. But let's zoom out for a moment and talk about something bigger. What does all of this mean for the Big Bang itself? The Big Bang theory is one of the most successful scientific theories ever. It explains the cosmic microwave background, the abundance of light elements, the expansion of space, the evolution of structure. It's been tested and refined over decades. But the Big Bang theory doesn't actually explain what banged, why it banged, or what happened before it banged. Inflation, proposed by Alan Guth in 1980 and refined by Andre Linde, Paul Steinhardt, and others, tries to answer some of these questions. Inflation suggests that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, growing from smaller than an atom to larger than a galaxy in 10 to 32 seconds. This sounds absurd, but inflation solves several major problems. It explains why the universe is so uniform on large scales, why it's geometrically flat, and why we don't see magnetic monopoles and other exotic particles predicted by particle physics. Inflation also predicts that quantum fluctuations during this exponential expansion would be stretched to cosmic scales, creating the tiny density variations that eventually became galaxies and clusters. When we measure the cosmic microwave background, we see exactly the pattern of fluctuations inflation predicts. It's one of the theory's greatest successes. But inflation also creates new problems. What caused inflation to start? What made it stop? The inflattened field, the hypothetical field driving inflation, has never been detected or connected to any known field in particle physics. Inflation is a placeholder, an idea that works mathematically but has no physical mechanism we understand. And some versions of inflation, like eternal inflation, suggest that once inflation starts, it never fully stops. It continues infinitely in some regions, constantly creating new bubble universes, while ending in specific bubbles like ours. This leads to the multiverse, an infinite ensemble of universes with different physical laws, different constants, different histories. If the multiverse is real, it raises profound questions about what we can ever hope to understand. The laws of physics in our universe might be arbitrary, just one possibility among infinite others. The constants that allow life to exist, the fine-tuning that makes stars and planets and chemistry possible, might be pure chance. In an infinite multiverse, everything that can happen does happen somewhere. Some physicists embrace this. Others hate it because it seems to end the possibility of a unique, elegant explanation for why our universe is the way it is. If anything is possible in some bubble, we can't explain why our bubble has the specific properties it has. It's like asking why you were born in the specific time and place you were. There's no deeper reason. It just happened. But here's where James Webb enters the picture again. If the early universe looked different than we thought, if structure formation was faster, if the timeline is off, inflation might need to be modified. The initial conditions, the fluctuations seeded during inflation, might have been different. Or maybe inflation itself happened differently, or not at all. There are alternative theories to inflation. Cyclic models where the universe goes through repeated cycles of expansion and contraction. Bouncing cosmologies, where the Big Bang was a rebound from a previous collapsing phase. Emergent universe models, where the cosmos existed in a stable state before beginning expansion. None of these alternatives are as developed or successful as inflation at explaining observations, but they're being reconsidered in light of the anomalies piling up. What I want you to understand is this: cosmology is in flux. The next decade of observations from James Webb, from the upcoming Nancy Grace Roman Space Telescope, from new ground-based observatories, will either confirm our models or shatter them. We're living through a pivotal moment in human understanding of the cosmos. And it's not just academic. These questions matter. Understanding the universe's origin, evolution, and fate is part of humanity's fundamental quest to understand our place in existence. Are we an accident? A random fluctuation in an infinite multiverse? Or are we part of a cosmos with deeper meaning, deeper structure? I'm not talking about religion here, though these questions obviously intersect with spiritual and philosophical worldviews. I'm talking about the human need to know where we came from and where we're going. Science provides one framework for approaching these questions, and when that framework starts cracking, it affects how we see ourselves. Think about the impact of previous cosmological revolutions. When Copernicus displaced Earth from the center of the universe, it fundamentally changed humanity's self-conception. We weren't special. We were on a planet orbiting a star like countless others. When Hubble showed the universe was expanding, it opened the possibility of a beginning, a moment of creation that could be studied scientifically. It brought cosmology from philosophy into physics. When we discovered dark energy, we learned the universe's fate was accelerating expansion, eternal isolation, heat, death. That's a specific answer to an ancient question. How does everything end? Each of these discoveries changed not just scientific models, but cultural narratives, philosophical frameworks, existential perspectives. What will it mean if we discover the Big Bang wasn't the beginning? That the universe is older, stranger, more complex than we imagined? That the laws of physics might be different in different cosmic epochs or different regions? It means our story needs to be rewritten. And humans are storytelling creatures. We need narratives that make sense of existence. When science disrupts those narratives, it creates both crisis and opportunity. Here's what you should be feeling right now, an hour and 20 minutes in. A mix of excitement and unease. Excitement because we're potentially on the verge of major discoveries that will reshape our understanding. Unease because the solid ground you thought science provided is revealed to be more provisional than you realized. That's okay. That's the right response. Science isn't about certainty. It's about the best current explanation given the evidence, with the understanding that new evidence can overturn everything, and new evidence is pouring in. Let me tell you about one of the strangest discoveries Webb has made, something that doesn't get enough attention in popular coverage because it's technical and hard to explain, but it's potentially revolutionary. The discovery of galaxies with weird chemical compositions. When we analyze the light from galaxies, we can determine what elements they contain based on spectral lines, the unique fingerprints of each element. We expect early galaxies to be mostly hydrogen and helium, with traces of heavier elements from the first few generations of stars. But Webb has found some early galaxies with unexpected chemical abundances. Too much nitrogen relative to oxygen, too much carbon relative to iron, ratios that don't match our models of nucleosynthesis, the process by which stars create elements. Nucleosynthesis is complicated. Different elements are created by different processes. Massive stars create oxygen and silicon in their cores and scatter them when they explode. Intermediate mass stars create carbon and nitrogen through different fusion pathways. Neutron star mergers create gold and platinum and the heaviest elements through rapid neutron capture. Over time, as multiple generations of stars live and die, the chemical composition of a galaxy evolves in predictable ways. We can model this. We can match models to observations for nearby galaxies. It works. But these early Webb galaxies don't fit the models. Their chemistry suggests stellar evolution pathways we don't understand, or stellar populations that don't match our assumptions. Why does this matter? Because chemical evolution is tied to stellar evolution, which is tied to galaxy evolution, which is tied to dark matter and structure formation. If one piece is wrong, the whole interconnected model is in question. It's like pulling on that thread again, watching the sweater unravel. Yuichi Harikon, a Japanese astronomer working with Webb data, found galaxies with emission lines indicating massive stars forming at incredible rates, creating heavy elements faster than should be possible. The star formation efficiency, the rate at which gas turns into stars, is near theoretical maximum in some of these early galaxies. In our current universe, star formation is messy and inefficient. Only a small percentage of a gas cloud becomes stars. The rest is blown away by stellar winds, supernova, radiation pressure. But in the early universe, maybe conditions were different. Maybe gas clouds collapsed more efficiently. Maybe feedback processes that limit star formation today didn't operate the same way. Again, every explanation requires us to add new physics, new conditions, new exceptions. Or, and this is the possibility that's both thrilling and terrifying, maybe our entire framework is wrong. Maybe stars don't form the way we think. Maybe galaxies don't evolve the way we model. Maybe the early universe was governed by processes we haven't even conceived of. At this point, you might be wondering, how can scientists function when their models are falling apart? How do they keep working when the ground keeps shifting? The answer is, the same way humans have always functioned in the face of uncertainty. You keep observing, keep measuring, keep testing hypotheses, keep refining theories. You live with ambiguity. You accept that knowledge is provisional, and you remember that being wrong is how science progresses. Every major breakthrough in history came from someone realizing the old model was wrong and proposing something new. Galileo overturned Aristotelian physics. Newton unified terrestrial and celestial mechanics. Einstein replaced Newton with relativity. Quantum mechanics replaced classical determinism with probability. Each revolution came from observations that didn't fit the old framework. We might be living through the next revolution. And if that's the case, someone watching this video right now, someone in the next generation of scientists, might be the one who figures out the new framework. That's the opportunity in crisis. That's the excitement in confusion? Let me give you your next retention hook. What if I told you that the weirdness James Webb is finding might be connected to the weirdness of quantum mechanics? That the early universe was so small and so energetic that quantum effects dominated, and we might need a theory of quantum gravity, uniting general relativity and quantum mechanics to explain what we're seeing? That's coming up, and it's going to bend your brain in new ways. But first, let's talk about what all of this means for you personally, because we're approaching the 90-minute mark, and it's time to connect these cosmic mysteries to your daily life and worldview. This isn't just abstract science. This is about what it means to be human in a universe that's stranger than we imagined. You've been alive during a remarkable period in human history. In the past few decades, we've gone from vague speculation about exoplanets to confirming thousands of worlds orbiting other stars. We've detected gravitational waves, confirming Einstein's century-old prediction. We've imaged black holes. We've sent rovers to Mars and probes to the outer solar system. And now, we've built a telescope that can see back to nearly the beginning of time and discovered the universe doesn't make sense. What does that mean for you? On one level, it doesn't affect your daily life at all. You'll still wake up tomorrow, eat breakfast, go to work or school, interact with people, live your life. The expansion rate of the universe has no direct bearing on whether you pay your bills or call your mom or pursue your dreams. But on a deeper level, it affects everything. Because humans don't just live in the physical world. We live in a conceptual world, a world of meaning and narrative. And the story we tell about the universe is part of the story we tell about ourselves. For most of human history, we thought we were the center of everything. The Earth was stationary, and the heavens revolved around us. Then we learned we're on a planet orbiting a star. Then we learned our star is one of hundreds of billions in a galaxy. Then we learned our galaxy is one of hundreds of billions in the observable universe. Each step was a demotion, a reduction in cosmic significance. We're not special. We're not central. We're an insignificant speck in an incomprehensibly vast cosmos. But there's another way to look at it. We're the universe becoming conscious of itself. We're matter that has organized itself into brains capable of understanding matter. We're stardust that can contemplate stars. The atoms in your body were forged in stellar furnaces billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all created in nuclear fusion or supernova explosions. You are literally made of the cosmos. And now, using those atoms arranged into neurons and synapses, you're capable of understanding cosmology, quantum mechanics, general relativity. You can comprehend ideas that transcend everyday experience. You can think about the Big Bang, infinity, the nature of time. That's extraordinary. That's perhaps the most remarkable fact about the universe. It has produced beings capable of understanding it. But here's where it gets philosophically tricky. What if we can't fully understand it? What if the universe is too complex, too strange, too vast for human minds to completely grasp? We've made incredible progress. Newton gave us mechanics. Maxwell gave us electromagnetism. Einstein gave us relativity. Quantum mechanics gave us the standard model of particle physics. We can explain an enormous amount. But there are fundamental limits to knowledge. Gödel's incompleteness theorems prove that any sufficiently complex formal system contains true statements that can't be proven within the system. Heisenberg's uncertainty principle shows there are fundamental limits to what we can simultaneously know about particles. And now, James Webb might be showing us limits to our cosmological knowledge. We can measure the Hubble constant two different ways and get incompatible answers. We can observe galaxies that shouldn't exist according to our best theories. We can infer the existence of dark matter and dark energy without being able to detect or understand them. Maybe the universe is, at some fundamental level, not fully knowable by beings like us. Maybe we're like ants trying to understand calculus. We can observe patterns, make limited predictions, but the full picture is beyond our cognitive capacity. Or maybe we're on the verge of a breakthrough that will unify everything. A theory of quantum gravity that combines general relativity and quantum mechanics, explains dark matter and dark energy, predicts cosmic evolution correctly. A theory of everything. String theory has promised this for decades. Loop quantum gravity offers an alternative approach. Other theories are being developed, but so far, none have been confirmed by observation. We have mathematical frameworks that might work, but no experimental evidence. And here's the kicker. Even if we develop a theory of everything, it won't answer the deepest questions. Why does the universe exist rather than nothing? Why these laws of physics and not others? Why is there something rather than nothing? Physics can't answer why questions, only how questions. Science describes regularities, mechanisms, causes within the universe. But it can't explain why there's a universe for science to describe. That's where philosophy, theology, metaphysics enter. That's where personal meaning comes in. Some people find meaning in the idea that the universe is purposeful, created by a higher power with intention. Others find meaning in the opposite, that the universe is random, and we create our own purpose. Still others find meaning in the search itself, a pursuit of understanding regardless of whether we reach final answers. What James Webb's discoveries should do, regardless of your worldview, is inspire humility. Intellectual humility, the recognition that our knowledge is limited and provisional. Cosmic humility, the recognition that we're small in space and time. And existential humility, the recognition that the universe owes us neither comprehensibility nor comfort. But here's the beautiful paradox. Recognizing our limitations doesn't diminish us. It elevates us. Because we're the beings capable of recognizing our limitations. We can stand on Earth, look out at billions of galaxies, detect the cosmic microwave background from 13.8 billion years ago, and say, we don't fully understand this yet, but we're working on it. That capacity for self-reflection, for questioning, for revising our beliefs in light of new evidence is what makes us human at our best. Think about your own life. How often do you hold beliefs confidently, only to encounter evidence that challenges them? It's uncomfortable, right? It's easier to ignore the evidence, to rationalize, to dig in. But growth comes from being willing to say, I was wrong. I need to update my understanding. That's true in personal relationships, in careers, in politics, in every domain of life. And it's true in science. Cosmologists are living through that discomfort right now. Decades of confident assertions about cosmic expansion, structure formation, the timeline of the universe, are being challenged. It would be easy to dismiss Webb's observations, to explain them away. But that's not how science works at its best. At its best, science is a communal process of error correction, where no authority is final, no theory is sacred, and evidence is king. That doesn't mean every fringe idea is taken seriously. It means extraordinary claims require extraordinary evidence, but when that evidence arrives, we must follow where it leads. And the evidence is leading us to a place where we have to admit, we don't know what most of the universe is made of. We don't know why it's expanding the way it is, and we don't know if our timeline is correct. That's okay. That's exciting. That means there's still so much to discover. Now, let me ask you something personal. How does this make you feel? Are you energized by the idea that our understanding is incomplete, that there are mysteries left to solve? Or does it make you anxious that the ground beneath scientific knowledge isn't as solid as you thought? There's no right answer. Both responses are valid. But I'd encourage you to lean into the discomfort. Because discomfort is where learning happens. Comfort is where stagnation happens. You're almost 2 hours in. You've stuck with this journey through some of the most challenging ideas in modern cosmology. That says something about you. You're not content with easy answers. You're willing to sit with complexity, ambiguity, uncertainty. That's a rare quality. Most people prefer simple narratives, clear answers, confident assertions. But reality doesn't owe us simplicity. And the universe we're discovering is anything but simple. Here's what's coming next. We're going to explore the most mind-bending implications of these discoveries. The simulation hypothesis, the anthropic principle, the multiverse. The possibility that consciousness plays a role in quantum mechanics and cosmology. These ideas sit at the intersection of science and philosophy, and they're being taken seriously by leading physicists because the weirdness of reality demands weird explanations. But I need you to do something first. Take a break if you need to. Stretch, get water, process what you've learned so far, because the second half of this journey goes even deeper. And once you step through that door, there's no going back. Welcome back. Let's talk about the simulation hypothesis. In 2003, philosopher Nick Bostrom published a paper arguing that at least one of three propositions must be true. 1. Civilizations like ours go extinct before developing the technology to run detailed simulations of conscious beings. 2. Advanced civilizations have no interest in running such simulations. Or 3. We are almost certainly living in a simulation. His reasoning is straightforward. If advanced civilizations can run detailed simulations of universes with conscious inhabitants, and if they choose to run many such simulations, then the vast majority of conscious beings would be simulated rather than real. If there are billions of simulated universes for every base reality, the odds are you're in a simulation, not the base reality. This sounds like science fiction, but it's taken seriously by physicists and philosophers. Why? Because the universe exhibits certain features that are consistent with being a simulation. Quantum mechanics operates on discrete, quantized values. Energy comes in packets called quanta. Particles have specific states. There's a minimum distance, the Planck length, below which our physics breaks down. It's like the universe is pixelated at the smallest scales, similar to how a computer simulation renders reality using discrete pixels or voxels. The speed of light is constant, like a maximum frame rate in a simulation. The laws of physics are mathematical, describable by equations, almost like code running a program. And here's where it connects to James Webb's discoveries. If we're in a simulation, the programmers might not have simulated the entire history of the universe in detail. They might have created a compressed backstory, generating just enough detail to be convincing to observers in the present epoch. Those early massive galaxies that shouldn't exist? Maybe they're artifacts of lazy world building, inconsistencies in the backstory. The Hubble tension? Maybe it's a bug, an error in how two different simulation subroutines calculate the same value. Now, before you think I've lost my mind, let me be clear. I'm not saying we are in a simulation. I'm saying the hypothesis is taken seriously because it makes testable predictions and addresses some of the weirdness we observe. If we're in a simulation, we might be able to detect glitches, anomalies that reveal the underlying computational structure. Some physicists have proposed looking for patterns in cosmic rays, regularities in the distribution of high-energy particles that would suggest a discrete underlying grid. Others point out that any sufficiently advanced simulation would be indistinguishable from base reality, so we'd never be able to prove we're simulated. The simulators would patch any glitches we discovered, or they'd restart the simulation, or we'd be incapable of recognizing the evidence, even if it was right in front of us. But here's what's philosophically interesting. The simulation hypothesis doesn't actually change anything about how we should live our lives. If this is a simulation, it's the only reality we have access to, so we might as well treat it as real. The physics works the same way. Our experiences are genuine within the context of the simulation. And if the simulators exist, they're presumably bound by their own laws of physics in their base reality. So the question just shifts up a level. What's the nature of their universe? Is it simulated too? You get an infinite regress unless there's a base reality somewhere. So why bring this up? because it illustrates how far modern physics has gone beyond common sense. We're discussing seriously whether the universe is a computer program, whether the Big Bang was the simulation booting up, whether the mysteries James Webb is revealing are features or bugs. This is where science becomes indistinguishable from philosophy and metaphysics. We're asking questions about the fundamental nature of existence using telescopes and equations. And that brings us to the anthropic principle, another idea that sits uncomfortably between science and philosophy. The anthropic principle states that the universe must be compatible with the existence of observers, because if it weren't, we wouldn't be here to observe it. That sounds tautological and useless, but it has profound implications. The constants of physics, the strength of fundamental forces, the masses of particles appear to be fine-tuned for life. If gravity were slightly stronger or weaker, stars wouldn't form properly. If the electromagnetic force were different, atoms wouldn't hold together. If the strong nuclear force varied even slightly, nuclei would fall apart, or all hydrogen would have fused into heavier elements in the Big Bang. There are dozens of these constants, and many of them fall within incredibly narrow ranges that allow for stars, planets, chemistry, and ultimately life. Change any of them by a tiny percentage, and the universe becomes sterile, unable to produce complexity or consciousness. This fine-tuning is weird. Why are the constants set to these specific values? One answer is the multiverse. If there are infinite universes with different physical constants, then some will randomly have the right values for life. We find ourselves in one of those because we couldn't exist in the others. It's selection bias. We observe a fine-tuned universe because that's the only kind of universe we could observe. But the multiverse is controversial. It's untestable, at least directly. We can't observe other universes by definition, so it's not clear if it's science or metaphysical speculation. Another answer is design. Some intelligence set the constants to allow for life. This is the argument from fine-tuning for the existence of God or a higher power. But this raises the question, who designed the designer? And it's not clear how to test this hypothesis scientifically. A third answer is that the constants aren't arbitrary. Maybe they're determined by a deeper theory we haven't discovered yet. A theory of everything that predicts the exact values from first principles. String theory hopes to do this, but so far, it predicts a landscape of 10,500 possible universes, not a unique solution. And here's where James Webb comes in. If the universe is older or different than we thought, it might change the fine-tuning argument. Maybe the conditions that allow for life are more common, less special than we believed. Or maybe they're even more rare and unlikely, reinforcing the mystery. The anthropic principle is frustrating because it seems to explain everything and nothing simultaneously. Yes, the universe must be compatible with our existence, but that doesn't tell us why this universe exists, rather than one of the infinite other possibilities. Some physicists argue the anthropic principle is a cop-out, a way to avoid seeking deeper explanations. Others argue it's a legitimate constraint on our theories, a recognition that observer selection effects are real and must be accounted for. What I find fascinating is how these questions have shifted over time. A century ago, we were debating whether other galaxies existed. Now we're debating whether other universes exist and whether we're simulated. Each answer leads to deeper questions. It's questions all the way down. And that brings us to consciousness, perhaps the deepest mystery of all. You are conscious. You have subjective experiences. You know what it's like to see red, taste coffee, feel pain. That inner experience, that qualia, is undeniable. Descartes' famous, "I think, therefore I am," starts from the certainty of consciousness. But we have no idea how consciousness arises from physical matter. How do neurons firing in specific patterns create the felt experience of being you? How does subjective experience emerge from objective processes? This is the hard problem of consciousness, articulated by philosopher David Chalmers. We can explain brain functions, how visual information is processed, how memories are stored. But we can't explain why those processes feel like anything. Why isn't it all happening in the dark, without any inner experience? Some philosophers argue consciousness is fundamental, not reducible to physics. Panpsychism suggests consciousness is a basic property of matter, like mass or charge, and complex consciousness emerges from the combination of simpler conscious elements. Others argue consciousness is an illusion, a trick the brain plays on itself. There's no hard problem because there's nothing to explain. The feeling of consciousness is just a functional state of information processing. But here's where it connects to cosmology and quantum mechanics. Some interpretations of quantum mechanics require observers to collapse wave functions, to turn potential into actual. Before measurement, particles exist in superposition, in multiple states simultaneously. Measurement collapses the wave function to a definite state. But what counts as measurement? Does it require consciousness? Or is any interaction sufficient? The Copenhagen interpretation, a standard textbook version of quantum mechanics, is vague on this point. It treats measurement as a special process without clearly defining it. This has led to endless debates and alternative interpretations. The many worlds interpretation says there's no wave function collapse. Instead, every quantum interaction causes the universe to split into branches, and all possible outcomes occur in different branches. You observe one outcome in your branch, but other versions of you observe other outcomes in other branches. This sounds insane, but it's mathematically consistent and solves some problems in quantum mechanics. It also implies an infinite multiverse, not of different universes with different laws, but of different branches of our universe, where different quantum outcomes occurred. If many worlds is correct, there's a branch where dinosaurs weren't wiped out by an asteroid and evolved into intelligent beings. There's a branch where you made different choices at every moment of your life. There's a branch where the Earth never formed. Every quantum event splits reality into all possible outcomes. The multiverse isn't elsewhere. It's here now, constantly branching with every particle interaction. Again, I'm not saying this is true. I'm saying it's a serious interpretation, taken by many physicists, because quantum mechanics is weird, and no interpretation is without problems. And here's the connection to cosmology. The early universe was quantum. When it was smaller than an atom, quantum effects dominated. The fluctuations that seeded galaxies were quantum fluctuations, stretched to cosmic scales by inflation. To fully understand the Big Bang, we need a theory of quantum gravity, combining general relativity, which describes gravity and spacetime, with quantum mechanics, which describes the subatomic world. We don't have that theory yet. String theory and loop quantum gravity are attempts, but neither has been confirmed. And without quantum gravity, we can't rigorously describe what happened in the first 10 to 43 seconds after the Big Bang, the Planck epoch, when the universe was so small and dense that quantum gravitational effects were crucial. James Webb is observing the universe only a few 100 million years after the Big Bang, but that's an eternity compared to the Planck epoch. We're seeing the aftermath, not the event itself. But what we're seeing might give us clues about those earliest moments. If structure formation was faster than we thought, maybe quantum fluctuations were larger. If the expansion rate was different, maybe inflation was different. If dark energy was stronger or weaker in the early universe, maybe it's connected to quantum fields we don't understand. Every mystery connects to every other mystery. Quantum mechanics, gravity, cosmology, consciousness, all intertwined in ways we're only beginning to glimpse. You're 2.5 hours in. We're approaching the final stretch. Here's what's coming. I'm going to tie all of this together, connect James Webb's discoveries to the biggest questions humans have ever asked, and leave you with something that will change how you see your place in the cosmos. But first, retention hook. What if I told you that the universe might be conscious, that the cosmological principle suggesting the universe is the same everywhere might extend to consciousness being a fundamental property of reality. That's speculative, at the edge of science and philosophy. But after everything you've learned, you're ready for it. Stay with me. The finale is going to reframe everything. Let's talk about emergence. It's one of the most important concepts in understanding reality, and it's going to help us make sense of everything we've discussed. Emergence is when complex systems exhibit properties that their individual components don't have. Water molecules aren't wet. Wetness emerges from billions of molecules interacting. Neurons aren't conscious. Consciousness emerges from networks of neurons interacting. Emergence is everywhere. Temperature is an emergent property of molecular motion. Solidity is emergent from quantum fields. Biology emerges from chemistry. Society emerges from individuals. The universe itself might be emergent. Space-time might emerge from something more fundamental, quantum entanglement or information theory. Some physicists, like Eric Verlinde, argue gravity is emergent, not a fundamental force, but a consequence of entropy and information. If gravity is emergent, if space-time is emergent, then the universe James Webb is observing is an emergent phenomenon arising from a deeper layer of reality we don't yet understand. This is where quantum information theory comes in. Information, in the physics sense, might be the most fundamental thing in the universe. John Wheeler proposed it from bit, the idea that physical reality emerges from information. Quantum entanglement, where particles remain connected regardless of distance, can be understood in terms of information. When you measure one entangled particle, you instantly gain information about the other, even if it's across the universe. Einstein called this spooky action at a distance and was deeply uncomfortable with it, but experiments have confirmed it's real. Some physicists now think space-time itself emerges from quantum entanglement. In this view, the geometry of space, the distance between points, the curvature described by general relativity, all emerge from patterns of entanglement between quantum states. If this is true, the early universe, when everything was entangled on the smallest scales, might have had a very different structure than we're imagining. And as the universe expanded and entanglement became more sparse, space-time as we know it crystallized out. This could explain why the early universe behaved so strangely in James Webb's observations. We're looking back to an epoch when space-time itself was different, when the rules governing matter and energy were in flux. I realize this is getting very abstract, so let me bring it back to something concrete. Black holes. Black holes are regions of space-time where gravity is so strong that not even light can escape. They're predicted by general relativity and confirmed by observations. We've detected them through gravitational waves, through their effects on nearby stars, and we've even imaged the shadow of a supermassive black hole using the Event Horizon Telescope. But black holes create paradoxes that reveal the incompleteness of our theories. The black hole information paradox, proposed by Stephen Hawking, goes like this. When matter falls into a black hole, information about that matter seems to be lost. But quantum mechanics says information can't be destroyed. So what happens? Hawking proposed that black holes evaporate through Hawking radiation, slowly emitting particles and losing mass until they disappear. But if the information about what fell in is lost, quantum mechanics is violated. If it's not lost, general relativity is violated because it says nothing can escape a black hole. This paradox has driven decades of research. String theorists proposed black holes store information on their event horizons, the boundary from which nothing can escape, in a holographic way. The holographic principle suggests all the information in a volume of space can be encoded on its boundary, like a hologram encoding 3D information on a 2D surface. If the universe is holographic, then everything happening in our 3D space is encoded on a 2D boundary at the edge of the universe. We're living in a projection, a hologram, and the real information is on a distant surface. This sounds like the simulation hypothesis again, but it's different. It's saying our 3D reality emerges from 2D information, not that we're a computer program. And here's the kicker. Some solutions to the black hole paradox require information to leak out, for Hawking radiation to be non-random, for subtle correlations to preserve information. If that's true, black holes aren't perfect black. They're quantum objects with structure we're only beginning to understand. James Webb found supermassive black holes in the early universe. These objects are laboratories for extreme physics, where quantum mechanics and general relativity clash. Understanding how they formed, how they grew so fast, might require new physics that resolves the paradoxes. Every mystery we've discussed, the Hubble tension, early galaxies, dark matter, dark energy, fine-tuning, quantum mechanics, consciousness, it all connects. The universe is one system, and we're trying to understand it from the inside, using brains made of the very matter we're studying. That's both our limitation and our superpower. We're the universe observing itself, thinking about itself, questioning itself. And here's the profound realization. You are doing that right now. You watching this video, processing these ideas, are participating in the universe's self-awareness. Think about that. The atoms in your brain were forged in stars. Those atoms have arranged themselves into structures that can contemplate the Big Bang, quantum mechanics, the possibility of multiple universes. You are matter that has become conscious, and you're using that consciousness to understand matter. That's not trivial. That's miraculous, whether you believe in miracles or not. So what does this all mean? What should you take away from 3.5 hours of cosmological crisis and existential questioning? First, humility. We know less than we think we know. Our best theories are provisional. James Webb is showing us that the universe is stranger than we imagined, and probably stranger than we can imagine. Second, wonder. Despite our limitations, we've come so far. We can measure the age of the universe to within 1%. We can detect gravitational waves from black holes colliding 1 billion light years away. We can image galaxies from 300 million years after the Big Bang. That's extraordinary. Third, responsibility. We're the only species on Earth, possibly the only species in the observable universe at this moment, capable of understanding cosmology. That's a privilege and a burden. If we destroy ourselves, if we don't survive, the universe loses a perspective on itself. Carl Sagan called Earth a mote of dust suspended in a sunbeam. We're fragile, temporary, cosmically insignificant. But we're also the dust that knows it's dust, that can map the cosmos and ponder its origin. Fourth, connection. You're part of this story, not separate from the universe, observing from outside, but embedded within it. The carbon in your DNA, the calcium in your bones, the iron in your blood, stardust. The energy powering your thoughts, released by mitochondria oxidizing glucose, comes ultimately from sunlight, from nuclear fusion in the sun, from the same process powering every star. You are connected to the cosmos in the most literal, physical way possible. And finally, agency. The universe might be 13.8 billion years old, or it might be older. It might end in heat death, or it might collapse, or it might be cyclic. Dark matter and dark energy might be real, or we might need new physics. But regardless of cosmic questions, you have agency in your life. You can choose what to learn, who to be kind to, what to create. The fact that we don't understand 95% of the universe doesn't diminish the importance of the 5% where your life happens. In fact, it makes it more important. Because in a universe that doesn't care about you, you can care about each other. In a cosmos without inherent meaning, you can create meaning. James Webb's discoveries are humbling. They show us the limits of our knowledge, but they're also inspiring. They show us there's always more to discover, more mysteries to unravel, more questions to ask. Science is a never-ending conversation between humans and nature. We ask questions through experiments and observations. Nature answers through data. We interpret, revise our theories, ask new questions. The conversation continues. And you're part of that conversation now. You've spent 3.5 hours learning about the cosmos, grappling with ideas that challenge your assumptions. That's a gift you've given yourself, an investment in understanding. What you do with that understanding is up to you. Maybe you'll pursue science, contribute to the next generation of discoveries. Maybe you'll share what you've learned with others, spreading curiosity and wonder. Maybe you'll just see the stars differently from now on, knowing they're not just lights in the sky, but furnaces creating the elements that make up everything you've ever touched. Whatever you do, remember this: we're living in a remarkable time. We have telescopes that can see to the edge of the observable universe. We have mathematics to describe black holes and quantum fields. We have the privilege of asking questions our ancestors couldn't even formulate. And we're on the verge of answering some of those questions, or discovering that the questions themselves need to be reformulated. The universe James Webb is revealing is not the universe we expected. It's more massive, more structured, more complex in its early epochs than our models predicted. The expansion rate is uncertain. Dark matter and dark energy remain mysterious. But that's okay. That's where we are. And from here, we keep exploring, keep questioning, keep wondering. Because that's what humans do. We're the species that looks up at the night sky and asks, what is all that? Where did it come from? Where is it going? What does it mean? And even if we never get final answers, even if the universe is too complex for our monkey brains to fully comprehend, the asking matters. The search matters. You matter. Thank you for taking this journey with me. If this video changed how you see the universe, hit that like button. If you want to continue exploring these ideas, subscribe. And most importantly, comment below. Tell me what blew your mind. Tell me what questions you're left with. Tell me where you're watching from and what time it is. Because you're part of a global community of curious people who refuse to accept easy answers, who want to understand reality as it is, not as we wish it to be. The universe is not what we thought, and that's the most exciting discovery of all. Keep looking up, keep asking questions, keep seeking understanding. The cosmos is calling, and James Webb is showing us we've only just begun to answer.